Hi students, hope you all will be doing well. Today we're going to dive into something called errors and uncertainties. You know, every time we measure something, like anything at all, there's always this tiny bit of doubt about the real value. Now, this isn't about you messing up or making a mistake. Nope. It's a fundamental, totally unavoidable part of science. It's called uncertainty. And today, we're going to pull it apart and see exactly what it's all about.
All right, so here's our game plan. We're going to kick things off by talking about how to choose the right tool for the job. Then, we'll nail down what uncertainty actually is, figure out how to calculate it, and go over the super important rules for how you write it down. And to wrap it all up, we'll take a look at how those fancy digital meters deal with this stuff.
Okay, let's get right into it. The first big challenge that every single scientist faces is picking the right tool. I'm not kidding. The instrument you choose can literally be the difference between a fantastic, useful measurement and one that's, well, completely worthless. So picture this. I hand you a small steel ball, like a little ball bearing. Your mission, should you choose to accept it, is to measure its diameter. Now, what tool do you reach for? This choice is so important because it's going to determine just how much you can trust your final answer. Well, you've got a few options on the table. You could grab a regular meter rule, right? That'll get you to the nearest millimeter, which is okay. Or you could step up your game with a vernier caliper that's way better, getting you to 1/10 of a millimeter. But for a tiny little sphere like ours, oh yeah, there's a clear champion here, the micrometer screw gauge. This thing gets us down to 1/100th of a millimeter. It's a whole different level of precision. And just look at this thing. The way a micrometer is built is just so smart. You see that part that you turn, the thimble? That and the superfine screw inside are the magic here. They're what let you measure these incredibly small distances with so much confidence. It's really just a beautiful piece of engineering, built for one thing, precision. This whole idea of precision and choosing the right tool leads us perfectly into our next topic, defining uncertainty. This is a huge concept in science, you guys. It's basically how we put a number on that little bit of doubt that comes with every single measurement we ever make. Just check this out. Look what happens with our steel sphere when we use the different tools. With a simple ruler, we might get 12 plus or minus 1 millimeter. The vernier caliper tightens that up to 12.3 plus or minus 0.1 millimeter. And then the micrometer? Wow, 12.34 plus or minus 0.01 millimeter. See the pattern? The reading gets more and more specific, and that plus or minus number, that's our uncertainty. It just keeps getting smaller and smaller. We're zeroing in on the true value. So, that brings us to the official definition. Uncertainty is simply the range of values where the real measurement is likely to be. And listen, I'm going to say this again because it's so important. Uncertainty is not an error. It's not a mistake. You didn't do anything wrong. It's just the built-in wiggle room that comes from the limits of our tools and, let's be honest, our own eyes. Okay, so we know this doubt exists, but how do we actually work with it in our calculations? Well, there are two main ways we talk about it. We can talk about absolute uncertainty, that's the simple plus or minus number, or we can talk about percentage uncertainty, which is a really cool way to see how big the doubt is compared to the actual measurement. So, let's say you measure something and write down 46.0 plus or minus 0.5 centimeters. What you're really saying is, I'm pretty confident the true actual length is somewhere between 45.5 and 46.5 centimeters. See, it defines a range. And here's a great way to see those two concepts. On the one hand, you have the absolute uncertainty. That's just the straight up plus or minus value. So in our case, plus or minus 0.5 centimeters. Easy enough. But then you have percentage uncertainty. Here we're asking, how big is that 0.5 centimeters compared to the 46 centimeters we measured? Turns out it's about 1%. And that is super useful because it lets you compare the goodness of totally different measurements. And how do you calculate that percentage? Honestly, it's a piece of cake. You just take the absolute uncertainty, the small number, and divide it by the measured value, the big number. Then multiply that by 100%. Boom, you're done. It's just a ratio showing how big your doubt is compared to your measurement. This table is pretty handy. It shows you some typical uncertainties you'd expect to see for common gear in the lab. like a top pan balance, right? It's usually good to about 1/100th of a gram. Or a thermometer with 1-degree marks. You can usually estimate to about 1/2 degree. This just gives you a really good feel for the built-in limits you're working with from the get-go. All right, so we know how to find the uncertainty, but now comes the really important part, learning the rules for how to write it down properly. This isn't just about being picky. It's about speaking the same language as every other scientist on the planet. It's all about clear communication. And guess what? There are really only 2 golden rules you need to remember. They're super important. Rule number 1, your uncertainty should only have 1 significant figure. That's it, just 1. And rule number 2, the number of decimal places in your measurement has to match the number of decimal places in your uncertainty. They have to line up. Let's make that crystal clear with an example. Say you measure time and your uncertainty is plus or minus 0.1 seconds. Okay, see that? 1 decimal place. That means your measurement has to be written to 1 decimal place too. So 16.2 seconds is perfect. But writing 16 seconds? Nope, not enough detail. And 16.23? Whoa, that's too much detail. You're claiming a precision you just don't have. They have to match.
Okay, so everything we've talked about so far is great for things with scales you have to read by eye. But what about digital meters? You know, the ones that just give you a number on a screen? Well, they have their own way of handling uncertainty, and it's a little different.
Now, the cool thing about most digital instruments is that the manufacturer has already figured out the uncertainty for you. It's built right in. You don't have to guess or estimate anything. You just have to do one thing: read the manual. And in that manual, you might see a phrase that looks a little weird at first. Something like this: uncertainty may be quoted as +1% plus 2 digits. Don't let it intimidate you. All this means is you have to calculate 2 little pieces of the uncertainty and then just add them up. Let's break it down with an actual reading. Say 4.00 volts. So first, we do the percentage part. What's 1% of 4.00 volts? That's 0.04 volts. Got it. Next, the digit part. When it says 2 digits, it means 2 counts of the very last decimal place. Our reading goes to the 100th place, so that's 2 times 0.01, which is 0.02 volts. The last step, just add them together. 0.04 plus 0.02 gives us a total uncertainty of plus or minus 0.06 volts. See? Not so bad. All right, let's wrap this up. What are the big things to take away? First, always choose the right tool for the job. Precision matters. Second, remember that every single physical measurement has some uncertainty baked right in. Third, when you report your numbers, follow the rules for decimal places so everyone's on the same page. And finally, when you're using a digital meter, don't forget to check what the manufacturer says about its uncertainty. So I want to leave you with this one thought. Now you know that every measurement has a doubt, a range of possibilities. So how is this going to change how you see the data all around you? When you see a news report, a scientific study, a poll, anything with a number, will you remember there's always an uncertainty there, hiding just under the surface? It's something to think about. Thanks for your attention today, and I look forward to our next lesson.
Important keywords for this topic appear on the screen, sorted according to various exam boards. These terms require focused study as they are very important and must not be neglected under any circumstances. Furthermore, a detailed past paper analysis is included for each board and paper format. Pay attention to this section as it will greatly improve your preparations. In addition, try to understand each keyword in context instead of memorizing them individually. Regular practice using these keywords in past questions will enhance your accuracy and overall exam performance.
Please subscribe our channel to get more educational videos. Thank you.